All right, so this is chapter 11 on analysis of variance. That's what ANOVA stands for. Another word for ANOVA is F-test, the statistic that we'll be dealing with in this chapter. We've dealt with Z, we've dealt with T for a long time now, and F. And based on my experience as a researcher, I would say analysis of variance is probably the most used out of all of these test statistics in actual science experiments and statistical analyses. ANOVA is pretty darn common. And in fact, ANOVA can do just about everything that a t-test can and more. So ANOVAs are quite valuable. The reason why ANOVAs are particularly important is that they can analyze, they can compare means when there are three or more means. If you think about the t-tests that we've done recently, the independent samples t-test and the paired samples t-test, both of those involve analyzing means in an experiment where we have one independent variable with two levels. The independent samples t-test is when we have one between subjects variable, independent variable with two levels. The paired samples t-test is when we have one within subjects variable with two levels. But in both cases, for both types, independent samples and paired samples t-test, single factor, single independent variable with two levels. And we're comparing those two means with the t-test. The F-test can actually do that too. The F-test, if you want to compare the ANOVA, if you want to compare a experiment with two means, you could actually use the ANOVA to do that as well. But if you want to analyze an experiment that has three or more means, that has more than two, that is three or more means that are compared three or more conditions, you have to use ANOVA. And the reason why has to do with multiple comparisons. The book does a decent job talking about this, and I encourage you to take a look, if you haven't already, as to what the book says about multiple comparisons. The idea is that if you have a study with like one factor with three levels, I think I have an example here. Yeah, here would be an example of a study with one factor with three levels. So here, the independent variable, the factor would be called something like type of distraction or amount of distraction, something like that. And this is when people are just driving normally, no phone, compared to driving with a handheld phone and a hands-free phone. So these are three different conditions. And then you can imagine that these scores down here are like how well you do on some obstacle course for driving. So we're measuring the dependent variable as your score on some type of a driving test. The independent variable, that is the factor, is the type of distraction. And there's three levels here. There's three conditions in the study. And so we can't just do a t-test here anymore, because t-tests only work up to two conditions. You can compare means for two conditions in a t-test, and that's it. Now we have three conditions, and we need to use ANOVA. And the reason why ANOVA is important, I mentioned on the previous slide, is because, in theory, one approach you might think about is, well, t-tests can compare two means. An independent samples t-test can compare two means. So we might be tempted to do a t-test right here to compare these two conditions. And then another t-test to compare these two conditions. And then a third t-test to compare these two conditions right here. So that would be three t-tests if you wanted to do each possible pairwise comparison among these three levels. That would require three t-tests. But the problem is that, and this is what the book does a good job explaining, and I think I explained it a little bit in the notes portion, is that as you use more t-tests, the likelihood of a false positive increases. So basically, the definition of alpha is the probability that we will get a false positive. Alpha usually is set at 5%. If you do one t-test, if you choose alpha as 5%, then that means the likelihood of you getting a false positive, That is, there really isn't a significant effect. There's no real phenomenon there, but your statistical analysis says there is. That's going to happen to you 1 in 20 times. That is 5% of the time. But if you do, that's just for one t-test. If you do three t-tests, then the likelihood of false positive increases with each t-test that you perform. And so what ANOVA basically is, it's a way of comparing all three or all of the means in your study. If you have a single factor with 3 levels, you're comparing all 3 of those means at the same time. If you have a single factor with 4 levels, you're comparing all 4 of those means at the same time. ANOVA is a way of comparing all of the means in your factor, even when there's more than 2, 3, 4, 5, 6. You can deal with any amount of means. It's a way of comparing all those means at the same time without having to do multiple t-tests. So it's a way of comparing the means that does not increase the likelihood of a false positive. This is what ANOVA does. When you do ANOVA, you can compare all 3 of the means of your factor at the same time, and your alpha level is still 5%. So here's this is from the book. This is like a figure that the book provides. And the idea is if you're just doing a bunch of t-tests, so if you have, I just showed you right here, if you have 3 means, like the example I just showed, that would require you to do 3 t-tests. If you're going to cheat and you're going to do a bunch of t-tests to compare the means, then that inflates your alpha. That increases the likelihood of a type 1 error, a false positive. It estimates, the book does, 14%, 14.3%. I don't know how the book comes up with these exact numbers. But instead of alpha being 5% like you want, if you do a bunch of t-tests, a bunch of multiple comparisons, your alpha level is inflated. The likelihood of a false positive is about 14%. If you do 4 means, that requires 6 t-tests. If you're going to do cheating and do a bunch of t-tests, which inflates your false positive rate to around 26.5%. Basically, the more means that you have in your factor, then if you're cheating and doing a bunch of pairwise comparisons with t-tests, then you have to do more and more t-tests, which gradually increases your false positive rate to unacceptably high levels. You always want it to be around 5%. And that's what ANOVA does. ANOVA is a way of comparing up to 7 means at the same time, even more. And the false positive rate is still going to be 5%. We're going to be comparing all of those means at the same time using ANOVA. So here's some kind of basic terminology about ANOVA. The term factor is used. I feel like I've been using this all semester. In fact, I believe I defined this probably in the very first day or the first week of school. But I want to remind you here, because when we're dealing with ANOVA, this is definitely the term that you see the most. I mean, yeah, when you look at like articles, they'll usually call them factors instead of independent variables. But basically, a factor is the IV or quasi-IV in a study. Factor means basically this is an independent variable or it's a quasi-independent variable. Statistically, IVs and QIVs are treated the same. So a factor is basically anything that is QIV or an IV. The levels are the individual conditions that make up the factor. In the example I just showed you, there was 3 different conditions. That is 3 different levels of the factor type of distraction. Here is some new terminology that you've never seen before. And this last one will definitely be more important if you take a methods class, research methods class. At least hopefully, if it's taught correctly, you will learn about Factorial Anova. In this class, we're only going to get up statistically talking about one-way ANOVA. One-way ANOVA is when your study has 1 factor, that is 1 independent variable. Like the example I just showed you, there was 1 factor type of distraction with 3 levels, 3 conditions. A factorial ANOVA, though, which is actually probably, it's more common in psychology at least than one-way ANOVA. Factorial ANOVA is when you have a study that actually has 2 or more factors, that is 2 or more independent variables or 2 or more quasi-independent variables. And these are actually some of the most powerful statistical tests in psychology. All of my published papers, for instance, the big findings come from Factorial Anova. And this is pretty common. The study I'm reviewing right now has several Factorial Anovas in both Experiment 1 and Experiment 2. Factorial Anovas are really the most common type of experimental analysis that there are, statistical analysis that there are. It's really much more common in psychology, at least, for there to be a study that has 2 or 3 factors, that is 2 or 3 independent variables instead of just one. But in this class, we're only going to get to Way Anova. And a lot of the principles from Way Anova can be extended to Factorial Anova, in at least some of the basic principles. Factorial Anova definitely has some things which are more complicated about it. But a lot of the basic stuff like p-values and et cetera that we've already learned about apply the same way to Way Anova and Factorial Anova. So now I'm going to show you an example, and we'll go through some calculations for Way Anova. So I'm going with the same example that I was just showing you several slides ago, where we're going to, this is a one way. One way means one factor. Something that's hard for students to understand. It's hard for me when I was an undergraduate. Eventually it sunk in. But, it gets confusing because there's all these different words, and there's multiple factors sometimes, there's multiple levels, and so these words get confusing. One way means one factor, one independent variable. Between subjects ANOVA means that the one factor that we have is between subjects. So the example we're going with here is the factor, the IV, is type of distraction with those same 3 conditions: no phone, handheld phone, hands-free phone. So those are the 3 conditions, the 3 levels of our factor type of phone distraction. And the dependent variable is driving performance. The better your driving performance, the higher your score. So that's the example. I think I have the data again right here. So pretty sure I actually have, in subsequent slides, I'm going to show you how we calculate F, which is the test statistic that we're going to be dealing with in this chapter, and how to make decisions regarding the significance of F, just like we did for t-tests and z-tests back in the day. We'll use this study right here. The sample size of this study, by the way, is 15. There are 5 scores in each condition. 5 times 3 is 15. So before we get into some calculations, talk about the null hypothesis and the research hypothesis for this. You notice this null hypothesis, it looks kind of similar to what we dealt with independent samples t-test. And independent samples t-test, I mentioned that there was kind of 2 ways of writing the null hypothesis. You could say for independent samples t-test, mu1 equals mu2. Or you could say for independent samples t-test, mu1 minus mu2 equals 0. Those are mathematically equivalent with just a little algebraic manipulation, moving the mu2 over, subtracting it over to the other side. But basically, so the simplest form of the null hypothesis for independent samples t-test, mu1 equals mu2. The reason you have 2 mu's for the independent samples t-test is because we have 2 conditions, condition 1, condition 2. Each condition has a mu, which is represented in the null hypothesis. Now for ANOVA, we have an example here with 3 conditions. The null hypothesis is basically, this is what happens if there's no significant difference, if there's no effect of the independent variable. So our null hypothesis, mu1 equals mu2 equals mu3. There it is right there. You have as many mu's as you have conditions in your independent variable. Here's the alternate hypothesis, or the research hypothesis. So this is when stuff gets kind of complicated, and it basically becomes virtually impossible to write the research hypothesis for ANOVA in a basic mathematical equality form where you have like equal signs and stuff. It becomes basically necessary to describe this in words because it's virtually impossible to write it out as an equality using an equation. So, the basic phrasing of a research hypothesis is that there is a difference. But in ANOVA, things are more complicated because we're not just comparing 2 things anymore. We can be comparing 3 things, or we might be comparing 4 things all at the same time. So there's kind of a couple. The research hypothesis is probably most concisely said here. There's at least one mean difference among the 3 groups, which can mean kind of 2 different things at the same time. It can mean all of the means are different from each other. That is, mu1 does not equal mu2, which does not equal mu3. Or that can mean some of the means differ from each other, but others do not differ. So it's possible, for instance, that mu1 does not equal mu2, but mu2 does equal mu3. That would be consistent with the research hypothesis. So the research hypothesis, there's at least one mean difference among the groups. A common mistake for undergraduates is to think that the research hypothesis is mu1 does not equal mu2, which does not equal mu3. That is wrong. That is one possible scenario that supports the research hypothesis when none of the means are equal to each other. But more generally, the research hypothesis is there is at least one mean difference among the groups. In this case, the example I've been giving, there's 3 groups. Sometimes there'll be 4 or 5 groups. In our current example, one mean difference among the 3 groups. So for instance, mu1 might equal mu2, but mu2 might not equal mu3. That would be consistent with the research hypothesis. So there's all these different possibilities. There's all these different scenarios that would support the research hypothesis. So instead of trying to list out all of those different scenarios, it's just easier to write it in word form. There is at least one mean difference among the groups. So please note, the null hypothesis can be written nice and concisely as an equation right here. mu1 equals mu2 equals mu3. But the research hypothesis cannot. The research hypothesis has to be stated in words. Any questions or comments so far? All right. Okay, so here's where we're getting into the calculations. The good news is that you guys aren't going to have to do really any calculations. I'm pretty sure, for instance, for homework 5, there's no ANOVA calculations. And for your test, there's no ANOVA calculations. There will be some conceptual questions about ANOVA. I was looking those over yesterday. There's definitely like 5 or 6 questions about ANOVA on the test, but none of them require you to do a calculation. If I recall, the written portion of your test requires you to interpret output from an ANOVA, which will start today and we'll finish next time, Wednesday. So you will have to interpret the output of an ANOVA, but you will not have to calculate one like you did for every other hypothesis test. You had to calculate T, you had to calculate Z. You're not going to have to do that. Which that's just kind of the course policy here at KU. Previous times when I've done statistics classes, I've definitely had my students calculate ANOVA, and personally, I think it is really fun. I guess not everyone shares my enthusiasm, but I think it's really fun. And I'm still going to show you some calculations just so you understand how it works, and it will help your conceptual understanding of what's going on if I work through some calculations. So I will be doing that. So one thing I want to point out here is the F equation right here. And so there's the F. This is equivalent to like the Z or the T statistic. So we've had the Z statistic, we've had the T statistic, now we have the F statistic. And there's some analogies. There's a lot of similarities between Z, T, and F. All of them are ratios. If you look, I have here is the T for the independent samples t-test. You notice this is a ratio. Ratio meaning that it's a fraction. There's a numerator on top and a denominator on bottom for T. And the same with F. It's a ratio, there's a numerator, there's something on top, and there's something on the bottom. For Z, T, and F, all 3 of those, it's always the numerator divided by the denominator. And that's not a coincidence. That's because all statistics are based on these ratios, the numerator divided by the denominator. And in all cases, Z, T, and F, the numerators and the denominators are doing basically the exact same thing. Mathematically, they're a little bit different, but conceptually, they're really not that different. They're all doing the basic same thing. So first, we'll talk about the numerator. It says here, basically what the numerator measured, whether we're talking about Z, whether we're talking about T, or whether we're talking about F, the numerator basically measures the influence of the treatment. Another way of, I think probably the easiest way of understanding this is thinking about it in terms of the independent samples t-test. You get a really big numerator when sample mean 1 and sample mean 2 are really far apart from each other. The numerator for T is basically this, subtracting these 2 means from each other. This number gets really, really big the further apart these 2 means are. So basically, the numerator of the t-test is measuring the magnitude of the difference between our two sample means. The numerator of the f-test does the exact same thing. We have 3 means now instead of 2. So we no longer are just subtracting M1 from M2, or we can't, and we're not just subtracting M1 minus M2 minus M3. We basically, the numerator here is measuring how far apart are the 3 means from each other. It's measuring the magnitude of the difference among the 3 means. Just like the t-test, the numerator was measuring the magnitude of the difference between 2 means. The formula is considerably more complicated when you have 3 means than it is for just 2. This is very simple, M1 minus M2, very simple. It's much more complicated to calculate the numerator MS between for the f-test. I will show you the formula, but you are not responsible for it here at this statistics class. So once again, numerator measures the influence of the treatment. Another way of saying that, the numerator measures the magnitude of the difference among the means. The denominator, on the other hand, measures the sampling error. Another way of saying that, because sampling error is kind of a complicated term, basically the denominator measures the amount of variability in each condition on average. We have, and the t-test, we have 2 conditions. And this thing, the standard error, which remember the standard error is standard deviation divided by the square root of n. Basically, standard error is a form of the standard deviation. It's the standard deviation divided by the square root of n, but it's a measure of variability. It's the amount of variability on average, and the t-test is the amount of variable on average in each of the 2 conditions. MS within, for f-test, is the amount of variability in each of the 3 conditions, or if you have a factor with 4 or 5, it's what is the average amount of variability in all of the various conditions of your study. So I'll show you some examples of how this works out in a second. One more thing that makes ANOVA a little bit more complicated than T is that in T, you just have 1 degree of freedom. And to remind you, for the 1 sample t-test, the formula for degree of freedom was n minus 1. For the paired samples t-test, the formula for degrees of freedom was n minus 1. For the independent samples t-test, the formula for degrees of freedom was n minus 2. When we're dealing with the F ANOVA, there's actually 2 types of degrees of freedom that we need to know. There's something called degrees of freedom between, also known as sometimes degrees of freedom numerator. And there's also degrees of freedom within, which is sometimes known as degrees of freedom denominator. So there's 2 degrees of freedom. And in these formulas, K means the amount of conditions in our study. So for instance, in the current example, when we've been dealing type of phone distraction, K equals 3. So our degrees of freedom between, that is our degrees of freedom numerator, is 3 minus 1, which equals 2. There's 3 total conditions, 3 minus 1 equals 2. The degrees of freedom within is the total sample size. In our current example, it's 15. We had 3 groups, each with 5 people in it. So the total sample size is 15 minus the amount of conditions, which is 3. 15 minus 3 equals 12. So our degrees of freedom between was 2. Our degrees of freedom within is 12. So those are the 2 different degrees of freedom that you have to calculate for F. Yeah, this is the stuff right here. You really don't need to know this. You don't need to know these formulas. What I do want you to know about MS between and MS within, once again, those things come from right here. MS between, which stands for mean square between. This basically measures the magnitude of the difference among the means of all of your conditions. MS within measures the amount of variable on average in each of the conditions. You don't actually need to know these formulas, but you don't need to know what MS between equals. You need to know what MS between is. You need to know what MS within is, but you don't need to know these equations because you will not have to do the calculations. So really, I'm just showing you this stuff for fun. You're not going to be required to know any of this, but these are the formulas that are used to calculate ms between and ms within. You have to calculate this, which is sum of squares, and it uses these formulas. They look really intimidating, but really, if you do practice with them, they're not. Oops. The book does talk about all of these. The book actually does a better job than most in talking about this one right here. A lot of textbooks will skip this one completely, but the book does a decent job of talking about this one. But these are the ways of calculating, once again, ms between, which is the numerator, ms within, which is the denominator. You have to use all of these things to calculate, and ultimately you get ms between right here and ms within right here. And then you can see ms between goes in the numerator, ms within goes on the denominator of your f ratio. So let's pretend that we've done some practice where we actually calculated f's. How are you going to interpret the f that you get? So there's some things which are different about f compared to t. And one of the things which is different about f compared to t is that f values are always positive. Because of mathematical reasons, which we're not going to have time to go into detail here, f is always possible, is always positive. I guess I'll say the reason, by the way, f is always positive is because all of the calculations of sum of f involve sum of squares. That is, mathematical calculations that involve squaring something. And when you're squaring something, it is impossible for that number to be negative, because any two numbers squared always equals a positive number. So f is always positive. Please note how this is different than z or t. Z can be negative, t can be negative, f cannot be negative. If you do a study and there's absolutely no difference among the condition means, for t or z, your statistic will equal 0. If there's no difference among your means for t or z, then your statistic will equal 0. For f, if there is no effect whatsoever, if there's no difference among all of the means of your various conditions, f is going to be 1. So this is different. Z and t, no effect means your z or t statistic is going to equal 0. For f, if there's no effect whatsoever, your f statistic is going to equal 1. If you do have a big effect, if you do, as basically the more you're more likely to have a significant effect, the further away your f gets from 1. That is, the bigger your f gets. So in this way, this is kind of the same as z and t, because for z and t, the further your test statistic gets away from 0, that is, the bigger your z and t statistic get, the more likely you are to reject the null hypothesis, the more likely you are to say that you have a significant effect. Same thing for f. The larger your f number gets, when you do the ratio, you divide the numerator by the denominator, you're going to get a number. It's going to be positive. The further away that number is from 0, the bigger the number is from 1 in particular, the bigger the number is compared to 1, the more likely you are to have a significant effect, the more likely you are to reject the null hypothesis. Questions or comments yet? We got a little bit more. Questions or comments? All right, good time. So let's keep on going. It's not chapter 12. Okay. So a couple summary of some things. How to use a F table. Actually, I think I'm going to talk about this more in detail next time briefly. I want to get to some calculations today. I will mention once again, if you have no effect at all, the F will be around 1, meaning no effect. The F will be 1. I also already said F ratios, because they're calculated based on variance, and variance involves sum of squares. Sum of squares involves squaring things, which makes things always positive. F ratios, the F number will always be positive, unlike T and Z, which can be negative. The F table, which I will show you how to use next time, requires both of these degrees of freedom. Remember for T, you had to know the degrees of freedom to look up your critical T value in your T table. Same exact thing for F, except for F, you're going to have to know 2 degrees of freedom. You're going to have to go degrees of freedom numerator, that is degrees of freedom between, and degrees of freedom denominator, that is degrees of freedom within. And I'll show you how to use that next time. So that's just something, we're going to skip over this for now, but I'll definitely take a look at that next time. I guess I should mention one more thing. When you look up the F table, just like you did in T, the number that that F table gives you is your critical F. If the F that you calculate based on MS between minus MS within, if that F number is bigger than the critical F you find in your F table, then you would reject your null hypothesis. That is, you would conclude that there's a significant difference. So just like what we did in the T table, you use the F table to find the critical statistic. And the statistic that you calculate using MS between minus divided by MS within, if that exceeds the critical F, then you reject the null hypothesis. Here's kind of a conceptualization of that. You could look up on a F table a critical F of 4.94, and then the critical region, the rejection region, would be F values that are bigger than 4.94. So this is kind of like the distribution. Please notice that it's there's only like one half of the distribution. When we were dealing with the T distribution and the Z distribution, it had a left side and a right side. It was symmetrical. That was because Z and T could be negative and they could be positive. When we're dealing with F, we only have a positive side of the distribution. So it's just the one, we're only looking at the one half, only one side of things. We're not looking at the left tail anymore. Now we only have one tail that we're dealing with, which makes things a little bit easier for F. That's one of the few things about F which is actually easier, is that we no longer have to worry about the left tail at all. So we'll come back to this next time as well. Okay, so here is, I'm going to calculate for you an F. And I'm going to do it for 3 different examples. Actually, I have 3 different examples of how to calculate F ratios. So once again, you're not actually going to calculate F ratios, but you are going to have to be responsible for understanding some conceptual things about F ratios. And so this is I've done these calculations for you, and it's over several slides to do all these calculations. So here's the example that we've been dealing with today. The type of distraction, 3 levels. The sample size N is 15. K equals 3 means that there's 3 levels. In case you're curious, that G means grand mean. So if you take the average of all 15 scores, the average score was 2. But we can also see the 3 sample means. So the sample mean of condition 1, right here, no phone, was 4. So this means when people are driving without a phone, they did very well on the obstacle course. They got a score of 4, which makes sense. When people are driving with a handheld phone, they scored relatively, it appears, worse. They only got a score of 1 on the obstacle course. And when they were driving with a hands-free phone, they're talking on a hands-free phone, they also did pretty bad. Their driving obstacle course score was 1. So we're using Nova to compare these 3 means. The 3 means, once again, are 4, 1, and 1. So I'm going to tell you that the answer is already 11.25. So when we actually calculate F for these data right here, we would get 11.25. And the reason we get that is because our MS between equals 15, and our MS within equals 1.3 repeating. And so if you do the math, 15 divided by 1.3 repeating, your F value gets 11.25. So you're never going to have to calculate these numbers, 15.1.3, and you'll never have to calculate the numerator, the denominator in this class. But I want you to understand basically what things influence the size of this. I've already said the numerator is influenced by the size of the magnitude of the difference among the 3 means. When there's a big difference between the 3 means, the numerator is going to be big. I think that's the one that's probably easy for people to understand. When the difference among these 3 means when the means are far apart from each other, the numerator is going to be big. The denominator, on the other hand, measures the average amount of variability within each condition. That's a little bit more difficult to understand. So I'm going to try and give you some examples that kind of illustrate this. First, I just want to prove to you I want to remind you, I want to show you how we got this 15 divided by over 1.33 repeating. So here I'm showing you how you calculate MS between. So you're not responsible for these calculations. But I guess I want to show you that the answer I got when I did the calculations was 15. And it involves using a sum of squares. So you're calculating a sum of squares number. And then ultimately you get this number, which is 15, which I put into the numerator right there. So I do these, MS between is MS numerator. It's the top part of the F ratio. When I did the calculations, I got 15. Here's where I show you how I calculated MS within. Once again, it involves sum of squares calculations. And then, so this is the sum of squares number that I got, 16. And then ultimately, when you do you apply the numbers to the mathematical formula, you get this number right here, MS within, and that's like mean square of the denominator. That's the denominator, the bottom part of your F ratio. It goes down here. So we did some calculations. We got 15 on top. This is the number that represents the magnitude of the difference among the 3 sample means. This number right here, 1.3 repeating, this represents the magnitude of this represents the average variability within each condition. If each condition has a lot of variability, if there's a lot of spread within each condition, then this number gets really, really big. But if the variability within each condition is small, then this number will be really, really small. So for instance, I want to do a practice. These are, I think, probably some of the more important types of little conceptual practice problems we could do regarding ANOVA. What would be, what would be an example? We could have 5 numbers that equal a mean of 4 with the lowest possible variability. What would be an example? What would be an example of 5 numbers that would have the mean of 4, but they would have virtually 0 variability? Can anyone figure this out? What would be 5 numbers that we could take the average of them, and when we do that, they're going to have literally 0 variability? Can anyone think about this? Anyone have an idea? 5 numbers that yeah, go ahead. I thought I heard someone.
All 5 of the numbers would equal 4.
Exactly. If you do that, if that was the same, if all 5 of the numbers here were 4, if all 5 of the numbers here were 1, if all 5 of the numbers here were 1, that means we would have literally 0 variability within each condition. And so that would make the denominator 0, which would actually make F infinite, which causes problems. But that never happens in real life anyway. So here we have relatively more variable. Yes, the least amount of variability you can possibly have is when every number in the condition is the same as the sample mean of that condition. The mean of condition 1 is 4. So you'd have 0 variability in this condition if all of these numbers were 4. The mean of this condition is 1. So you'd have 0 variability in this condition if all of these numbers here were 1. The mean of condition 3 is 1. You'd have 0 variability in this condition if all of these were 1. If that was the case, all of these were 4s, all of these were 1s, all of these were 1s, that would cause the denominator to be 0. That would be 0 variability. There'd be 0, the number 0 would be in the denominator because of 0 variability. So I'm really trying to emphasize the numerator is the magnitude of the difference among the sample means. The denominator is giving you the average amount of variability in each of the 3 conditions. Here our variability is 1.3, but I just talked about a scenario where the variability would be really, really small and the variability would be 0 if all of the numbers within each condition were the exact same as the mean of that condition. So here is another example. Here is another example using the same kind of idea. The data that I showed you for the first example were actual real data taken from an actual study. Now what I've done is I've manipulated the data as a teaching example. And the reason I'm doing this is because I want to show you how the MS between and MS within change depending on properties of the data. And so what I've done here is I've gone in, so I left this condition the same. So 4, 3, 6, 3, 4, that's the exact same as the old example. This is example 1 here, 4, 3, 6, 3, 4. And so here's example 2, the new example. This condition is the same, 4, 3, 6, 3, 4. The sample mean of this condition is still 4. But I've changed these numbers right here. So these numbers, the sample mean here is now 4. So this mean in condition in example 1, the mean of the handheld condition was 1. But basically what I've done is I've added 3 to each of these original numbers. The original numbers were 0, 1, 3, 1, 0. Now they're 3, 4, 6, 4, 3. It's the exact same as the first example, except I've added 3 to each number here, which means that the mean of this condition is also 3 higher. So this mean used to be 1, but now I've added 3 to each score, which makes the mean 3 higher. So now the mean of this condition is 4. And for this condition, I've added 2 to each score. So originally in example 1, the mean of this condition was 1. But now I've added 2 to each score. So originally these numbers were 1, 2, 2, 0, 0, but now, and the mean was 1. But now I've added 2 to each score. So now it's 3, 4, 4, 2, 2. And so the mean of this condition is 3. And so I want you to notice how the F ratio changes here. And one of the things that I want to point out is that when we look at the MS between, and I show you the calculations here, the MS between in example 1 was 15, a big number. The MS between now is 1.6 repeating. So MS between has gotten smaller. I want you to understand why. So think about that while I'm talking about MS within. Notice the MS within, though, has not changed. The reason the MS within has not changed, remember the MS within, this denominator, this measures the average amount of variability within each condition. In example 2, that is the amount of variability in each condition is constant. It is the same as it was in example 1. The reason it's the same is because I've added the same number to each of these scores. In this condition, I added 3 to each score. In this condition, I added 2 to each score. What that does is that keeps the variability within each condition the same. And so MS within is the same. But MS between has gotten smaller. The question I have for you, why is MS between smaller now? Originally in example 1, MS between was 15. Now it's 1.6 repeating. Why has MS between gotten smaller?
Because there's a smaller difference between the means of each condition.
Thank you. Excellent. Yes. Originally, the means were 4, 1, and 1, which is a relatively big difference. But now it's 4, 4, and 3. Those 3 means are clustered closer together. Originally, it was 4, 4, and 1, which is a relatively big difference among the means. Now, 4, 4, and 3, the means are closer together. There's less of an average difference among those 3 means than there was in example 1. I'll show you. Just 4, 1, and 1, relatively big difference among the 3 means. 4, 4, and 3, it's a relatively smaller difference among the means. Therefore, the numerator has gotten smaller as well. This is where we'll call it a day for today. We'll start off here. We'll go over the F table next time. We'll go over some SPSS outputs next time. And we'll also go over the study guide for your final test next time as well. And I'll remind you, your final test will be, I'll have it available for you this weekend, and you'll have all finals week to take it. If anyone wants to chat, we have some time before my next class at 10 a.m. I'm happy to help work on homework and stuff with people if you want to now, but you're free to go. Take off.